Welcome to This Explainer. Today, we're popping the hood to look at a kind of terrifying paradox. You know that VPN you trust to hide your identity? Well, it might actually be silently leaking your real IP address right this very second. We hear all the time about how absolutely crucial a VPN is for privacy. But there's this hidden mechanism operating your browser right now that can completely bypass all of that protection, and you wouldn't even suspect a thing. So why exactly does your VPN leak your IP? Picture this, you pay for a top-tier VPN, you flip it on, you see that little connected icon light up, and you feel totally secure, only to find out later that your real, actual home IP address is entirely exposed to the websites you're visiting. I mean, how is that even possible? It feels like a massive failure, right? But the truth behind why this happens is actually way more interesting than just a glitch or a broken app. It's a fundamental clash of technologies. Let's dive into this. On your screen right now, you're looking at two totally conflicting realities existing at the exact same time. On the left, your VPN client is confidently reporting one thing, a secure remote server IP. It's telling you, hey, you're protected. But simultaneously on the right, a protocol called WebRTC is reporting something entirely different, your actual real home IP address. Both of these are happening on the exact same website. And spoiler alert, this isn't a bug. It's not a VPN failure at all. The real culprit here is WebRTC, which stands for Web Real-Time Communication. Now, this is a browser API built specifically to connect browsers directly to each other, peer-to-peer, without bouncing your data through a central server first. And why do we need that? Because let's be real, nobody wants a 3-second delay when they're talking on Google Meet or gaming on Discord. WebRTC exists purely for speed. It prioritizes that lightning-fast direct connection to give you crisp, low-latency video and audio right there in your browser. But that whole direct connection thing? That is exactly where this gets incredibly complicated. You see, for two devices to form a direct link, they first have to know each other's actual reachable address. And that's pretty tough, considering most of our devices sit behind a router doing something called network address translation. Think of it like a massive corporate office building. Everyone shares one main street address, but they all have different internal extension numbers. Your computer doesn't just naturally hand out its public IP to anyone who asks, because honestly, most of the time, it doesn't even know it itself. And that brings us to a cleverly named protocol called STUN, or Session Traversal Utilities for NAT. Now, STUN doesn't route or store your heavy web traffic. Instead, it comically just acts as a simple mirror so your browser can see its own outside appearance. It's a super simple interaction. Your browser basically asks the STUN server, hey, what do I look like to the outside world? And the server replies, well, here's the exact public IP and port I just saw you connect from. Right, so once your browser has looked in that mirror, the ICE framework steps in. That's Interactive Connectivity Establishment. ICE acts kind of like a relentless postal worker. It takes every possible address it can find for your device and just methodically tests them in various combinations until it finds a successful, direct path between peers. It literally leaves nothing to chance. It just wants to find the absolute most efficient way to connect your device to someone else's. To make this happen, the ICE framework automatically builds a complete checklist of routing options, which are officially called ICE candidates. First, it grabs your local network IP, then your public IP, which it got from that stun mirror we just talked about, and sometimes it even grabs a fallback relay address. It meticulously records and tests every single one of these. It genuinely needs this entire checklist to guarantee that peer-to-peer connection won't fail, ensuring you get that smooth video call without a hitch. Now, here is the absolutely crucial takeaway from all this. Up to this exact moment, nothing has gone wrong. Literally nothing. This is just WebRTC operating perfectly, exactly as engineers designed it to facilitate those lightning-fast connections. Gathering these addresses is functionally necessary. It's not a design flaw. You just can't build a peer-to-peer bridge without knowing exactly where both shores are, right? The technology is doing its job beautifully. Well, as we're about to see, perfectly designed features can easily turn into privacy nightmares. Let's look at the invisible JavaScript exploit. We'll see how this innocent address gathering process actually gets weaponized into a full-blown IP leak. Because here's the thing, this entire sequence doesn't actually require you to be on a video call. There's no obvious pop-up to warn you. It all starts with JavaScript running quietly in the background of a web page, completely invisible to you while you're just browsing the web. Just look at how this silent collection works. Any web page out there, a news site, a random blog, a forum, can run a few invisible lines of code to generate a WebRTC connection object and just listen for those ICE candidates. It requires zero user permission.
You don't get a camera access prompt, no microphone pop-ups, nothing. A site can just sit there, completely bypass whatever your VPN says, and quietly harvest your real, local, and public IPs without you even knowing it asked for them. Crazy, right?
So why exactly does this bypass happen in the first place? Well, it's because normal web traffic and WebRTC's address discovery are operating on two entirely different layers. Think of your VPN as this highly secure encrypted pipe that's handling your normal HTTP and DNS requests safely. Meanwhile, WebRTC and stun traffic are over here using a completely separate, unencrypted pipe built on the UDP protocol. It is literally slipping right past the security checkpoint, taking an alternate route that the VPN just isn't policing in the same way.
And that creates a massive side channel. It's not a bug in the VPN, it's a side channel. Depending on your operating system and your browser, this WebRTC stun traffic simply ignores VPN routing rules entirely. It hands the website your real IP through a backdoor that the VPN was never actually designed to cover. Your VPN is doing exactly what it was programmed to do, but your browser is essentially sneaking behind its back to secure that fast peer-to-peer connection. Like I said, it's a structural blind spot. Thankfully, browser vendors haven't just ignored this side channel. They understand the massive privacy implications this creates for users who are just trying to stay anonymous online. So let's break down how modern browsers are actually fighting back to plug this specific leak, and, more importantly, what you can do right now to make sure you're protected.
So different browsers take different approaches here. Chrome and Edge use something called MDNS obfuscation, which basically tries to hide your local IP behind a random hostname. But that's really only a partial fix, because your public IP can still totally leak through. Firefox, on the other hand, they offer the nuclear option for complete privacy. You can actually dive into the about.config menu, find the peer connection setting, flip it to false, and completely shut down the WebRTC API at the browser level. It is highly effective.
But what if you don't use Firefox? Well, action is definitely required on your end. You can use dedicated VPN browser extensions, like the ones from ExpressVPN, NordVPN, or ProtonVPN, or you can use powerful ad blockers like uBlock Origin to restrict the API. But listen, here is the massive caveat that you absolutely must remember. None of these protections are turned on by default. 0. You have to actively go into your extension settings and manually toggle that WebRTC leak protection on. If you haven't checked this recently, you are very likely vulnerable. So bringing it all back to solve our opening paradox, there's no grand conspiracy here, and no, your VPN isn't broken. We are just looking at two separate systems operating at completely different layers, clashing on your machine. One system is meticulously trying to tunnel all your traffic securely to protect your identity. Meanwhile, your browser's WebRTC API is aggressively hunting for the fastest direct connection possible, completely unaware that it is blowing your cover in the process. Now that you understand the hidden mechanics behind this silent leak, knowing really is only half the battle. Your privacy is only ever as strong as your weakest configuration. So I gotta ask you, have you tested your own setup yet? Seriously, when was the last time you checked your browser's configuration? Don't just assume you're invisible because that VPN icon is green. Go test your setup today, take back control of your data, and ask yourself, what else might your browser be sharing behind your back?